All right, let's dig in. We're about to explore the invisible science that quite literally supports our entire world. It's the reason skyscrapers don't just sink into the ground, why massive dams hold back lakes, and why bridges can stand for centuries. And it all starts with one simple question.
I mean, really think about that for a second. We look up and we see the gleaming steel, all that reflective glass. But what if the most critical component is the one we never even see? What if the real engineering marvel isn't up there in the sky, but is happening right under our feet?
And that leads us right to the fundamental challenge, the absolute core problem that every single major construction project has to solve. Before a single beam is ever raised, engineers have to grapple with this one critical question.
Yeah, see, the ground isn't just a solid block waiting for us to build on it. It's this incredibly complex mix of materials that can shift, it can squeeze, and in some cases, it can even flow like a thick liquid. So, how in the world do you build a multi-ton skyscraper on that? Well, the very first step is to stop thinking of it as just dirt. To solve the problem, engineers had to completely deconstruct the idea of dirt. They had to start treating it not as a random substance, but as a complex material, and they had to learn to speak its language.
And this, right here, is the absolute key. This is the core idea of all of geotechnical engineering. The ground isn't random. It follows physical rules. And if you can understand those rules, you can build just about anything on it. So, what are the most important rules?
First up is something called the void ratio. Basically, it's just the amount of empty space you have between the solid bits of soil. Now, why does this matter? Well, if you have a high void ratio, lots of empty space, and you put a massive building on top of it, all that space is going to compress, and that can cause the entire structure to sink. Not good.
Porosity is a very similar idea. It just frames that empty space as a percentage of the whole thing. The best way to think about it is like a sponge, right? How much of that sponge is the actual sponge material, and how much is just holes? That's its porosity.
So what's filling all those empty spaces? A lot of the time, it's water. The degree of saturation tells us exactly how waterlogged the soil is, on a scale from totally bone dry to 100% full. And that one single factor, well, it changes absolutely everything. So by measuring these core properties, engineers can finally start to create some order out of what just looks like a chaotic mess of dirt. It lets them develop a shared language to describe and even predict how any given patch of ground is going to behave under pressure.
And having this shared classification system is absolutely crucial for safety and for making things predictable. I mean, you can't design the right foundation if you don't know if you're building on solid gravel or something more like squishy clay. You've got to have a reliable system.
One of the biggest factors is super simple. It's particle size. Are we talking about big, chunky, visible gravel? Or gritty sand that you can see the individual grains of? Or are we dealing with microscopic silt and clay particles that just feel smooth or even sticky when they get wet? This really simple difference has massive implications for how you have to design the foundation.
Now, to make all this official, engineers use standardized lab tests. They figure out the grain size distribution by literally sifting the soil through a bunch of sieves, and then they do these things called Atterberg's limits tests. It sounds fancy, but it's basically a way of finding the exact tipping point where a fine-grained soil goes from being a solid to acting like a moldable plastic putty to eventually flowing like a liquid. Okay, but just knowing what the soil is, that's only half the battle. The next step is to understand how it's going to react when you put the immense pressure of a building on top of it. And this is where the forces at play get really, really dynamic. So people mix these two up all the time, but the difference is critical. First, you have compaction. This is fast. Think of quickly packing a suitcase. You're just squeezing the air out to make everything fit. You see this on construction sites all the time with those big rollers. But then there's consolidation. This is a slow, gradual process, where the constant weight of a building squeezes the water out of the soil. It's like having a wet sponge at the bottom of that suitcase that gets slowly compressed over months or even years. This process is actually what causes buildings to settle over time. And the speed of that water squeezing process is all determined by the soil's permeability. Basically, how easily water can move through it. In something like sand, which is highly permeable, water flows out fast. But in a low permeability clay, it can take decades. Engineers can actually calculate this flow rate using a principle called Darcy's Law, which connects the water pressure to how quickly it can escape the soil. Okay, so we get the material, we have a classification system, we understand the forces. Now, let's put it all together and see how engineers create their actual blueprint for building on solid ground. The answer is a super rigorous scientific process. You don't guess, you investigate. Before any major project even breaks ground, a team of geotechnical engineers performs a really detailed site investigation to create a complete picture of the ground they're about to build on. So first, they'll explore the site's surface geology. Then they bring in the heavy machinery, massive augers and drills that pull up core samples, revealing all the layers of soil and rock deep below. And this is crucial. They collect special undisturbed samples that keep the soil's natural structure intact. Those samples then go back to the lab for all the tests we just talked about. And finally, all of this data, all this analysis, gets compiled into one incredibly important document, the geotechnical report. That report basically becomes the Bible for designing a safe, stable foundation.
So, the next time you see a skyscraper, or a bridge, or a massive dam, just take a second to remember the incredible science that's happening right underneath it. It's this constant negotiation between human ambition and the very ground we're standing on. And, it just makes you wonder, as our understanding of this hidden world gets even better, what amazing new structures will we be able to build?